Hello friends and welcome back. This video will be about a more general type of circular motion, not just uniform circular motion, but slightly more general, not crazy, but slightly more general. And in particular, so far, uniform circular motion, we talked about the angle phi, r being a constant, and this is still true. But we said that phi was equal to, well, proportional to time plus some phi naught, and this is no longer true if it's not uniform. And in particular, we called omega the first derivative of phi. This is the angular velocity. We can give a name to the second derivative of the angle, which is the first derivative of omega, and we call it typically alpha. And this alpha is the angular acceleration. Okay. The units are angle per time squared, so this would be something like radians over second squared in SI units, but any angle divided by time squared works. And if we have uniformly accelerated angular motion, circular or angular motion, then in a very analogous way to what we had for in linear motion, phi is none other than the initial value plus the initial value of the angular velocity times t plus 1/2 alpha t squared. This looks a lot like a lot, or equivalently, delta phi is omega naught t plus half alpha t squared. This looks a lot, I'm sure you can see it as a lot like x naught plus v naught t plus 1/2 a t squared, or delta x is v naught t plus 1/2 a t squared. It's exactly the same thing, but instead of having linear motion, we have angular motion. So the angle changes not just proportionally to time, but also quadratically with time, depending on the acceleration. All right. As it turns out, you can prove, but I won't ask you to. And so either go and look at your favorite textbook for the derivation, or try to do it yourself. It's not that complicated. That if you have non-uniform but accelerated circular motion, then the acceleration has the usual centripetal component plus a tangential component. So in general, it's not pointing always to the center. In general, it's not pointing towards the center. But it's also there's a tangential component, all right? And in particular, you can show that the centripetal acceleration is the usual, so this is always r omega squared, or v squared over r, where it's understood that omega is not a constant. So I need to calculate at each value of time, at each time. And the tangential component is r omega dot which is, by the way, just the change in speed. So if you're speeding up or slowing down potentially along the circle, then not only will there be a centripetal acceleration component, but a tangential component as well. Let's see if I can draw this and illustrate this quickly with an example. So imagine that I have my object, and this object is moving on this attempt of a circle. Let's say that this is the velocity in the moment that I'm looking at, and this is your position vector. So in uniform circular motion, then the only component of acceleration is the centripetal component that is pulling towards the center, and it has magnitude equal to r omega squared, where omega is d phi over dt as usual. In uniformly accelerated circular motion, it's a bit of a mouthful, but why not? So AC, so centripetal acceleration is still there, and it's the same amount. So if you know that an object is moving at a certain speed along a circle at a certain moment, then you always have centripetal acceleration. But this will have to be added to a tangential component, which depends on whether you're slowing down or speeding up. So if you're speeding up, then you also have a positive tangential acceleration, so that overall the would-be total acceleration is somewhere in this direction. This is for speeding up. In blue, if you're slowing down, then you'll have a tangential acceleration in the opposite direction as v, and so the acceleration vector will be somewhere in this direction. See, notice how the centripetal acceleration is still there, and it's always the same amount, and it doesn't matter if you're accelerating or not. It only depends on how fast you're going, angular velocity or speed. Whereas the tangential velocity, it does indeed depend on the change of speed or the change of angular velocity. Oh, this is, by the way, also equal to r alpha, because we called omega dot, so the second derivative of phi, we called it alpha. Okay. Yes, let's do a quick zoom out here and do a quick recap. Oh no, what did I do? This and this, maybe this. Very, very quick recap, or very quick consideration, which is 1. Do you have curved motion? There's always a centripetal acceleration, and this is always equal to r omega squared. Always. Where r is the radius of curvature of your motion. Do you have like speed up? Does the speed change? Then you always have a tangential component, and this is simply v dot, or for circular motion, r alpha. Okay, and v dot, careful, it's not only acceleration, it's the rate of change of speed. Okay. All right. Great, I think this concludes this brief video. Thank you for watching and see you soon.